This lecture is going to be on the second part of Focus 3B, which deals with entropy changes of specific processes. And what we'll be looking at now are phase transitions. So a phase transition is, for example, water going from a solid to a liquid, or from a liquid to a vapor. Right? So the normal transition temperature, TTRS, is going to be the temperature at which the two phases are in equilibrium at 1 atmosphere of pressure. And so, for example, for us, if we take that example of water, water is going to be in equilibrium between both a solid and a liquid at 1 atmosphere of pressure when the temperature of the system is at equal to 0 degrees Celsius. So we have this equilibrium between the two phases. So at this the temperature of transition, or the normal temperature of transition, the phase transition is actually inherently a reversible process because the system is in equilibrium between the two states. So using our solid-liquid example for water, an infinitesimally small addition of heat will shift the equilibrium that the entire system becomes liquid, but removing that infinitesimally small amount of heat will then shift the system back into equilibrium between that solid liquid and liquid states. So if this process occurs at constant pressure, that means we can substitute in our definition for enthalpy at constant pressure, which enthalpy at constant pressure is just equal to the amount of work done. The amount of heat transferred at constant pressure. So Q rev P is just going to be equal to the enthalpy change of the transition. The reason I have reversibility put in here is because at that transition, you're inherently at equilibrium. So where the enthalpy change of the transition is the molar, to be very specific here, this is actually the molar enthalpy of transition. So the units here would technically be kilojoules per mole. The reason I mention that is because most delta H's that you look up in literature will be in the units of kilojoules per mole. So if we substitute this new equation that we derived into the definition of entropy, we see that the molar entropy change of a phase transition is just equal to the molar enthalpy change of the transition divided by the temperature at which that transition is taking place. And this is good agreement what we know about entropy of solids versus liquids. So let's go back to our example of water freezing. So if you look up online at or in a book, a textbook, or some of the government published data, the molar enthalpy of the freezing of water is just going to be equal to negative 6,010 6,010 joules per mole. Then sign is negative because as something is freezing, it must be giving off heat as it lowers its enthalpy as it transitions from a liquid to a solid, right? So therefore, the molar entropy of freezing is just going to be equal to that delta H divided by the T, and we find out that the change in entropy when water freezes is negative 22 joules per mole per Kelvin. And this fits with our expectation of what we see when a compound freezes. Right, so you're going from something that is high energy like a liquid, high entropy like a liquid, where the water molecules have a higher degree of freedom to move past each other, and as they start to freeze, you're organizing this into a crystal lattice, which is going to be lower entropy, and is exactly what we see here in our equation. So our observations of reality match with our derived equations.